Myself, Manikandan, Associate Professor in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering. So today in the subject analysis of aircraft structures, so we're going to see the topic fluctuating stress. So already we have seen that what is impact strength due to axial bending and torsional loads, effect of inertia, so fatigue strength, and what are the parameters affecting the fatigue, what is high cycle fatigue, what is low cycle fatigue, and modifying factors. And now that fluctuating stress and Goodman and Soderbergh relationship, what is it that we will see today. So fatigue under fluctuating stress. So when there is multiple kind of combined load when it is acting and multiple during that real component, always the stress will be fluctuating. And so when a component is subjected to a fluctuating stress, the stresses are resolved into two parts. One is mean stress and stress amplitude. So mean stress and stress amplitude is nothing. So when you are having that already that while I'm explaining that stress cycle, I said is that your so stress will be having that your proper bending means will be having a tension, and if you are taking this as a mean line, right? So stress with respect to time, right? So when the time varies, that it will be stress will be having that your cycles. So one cycle and two cycles, then another proper bending. So proper bending means it's a proper tension. At the same time, equal compression also you will be getting that. So now two component there's a D, it is mean stress and stress amplitude. So mean stress is nothing. So from here, now this is at your sigma max. This is at your sigma minimum. So now the mean stress means it is sigma max plus sigma minimum divided by 2. That is at your mean stress. So another one is stress amplitude. So this is at your amplitude, right? So now this up to here it is sigma max, sigma minimum, and up to here it is sigma maximum. So now stress amplitude is the one side. This will be that your stress amplitude, and for the compression this is that your stress amplitude. So now what is that stress amplitude means? Sigma max minus sigma minimum divided by 2. So these two are the resultant. These two are the main parts for resolving the fluctuating stress. Right. So here you can see that in that graph we'll be having that all the kind of points in that fatigue. So we are plotting. So when you are having that, so due to that real component, you will be having that fluctuations in the stress levels. So due to that, what we will do, we'll be drawing a common line, so average line, so that each and every scientist, one person find out the lines. So one is Soderbergh line and a Goodman line and Gerber parabola, and these are your failure points. So due to that rotating beam testing machine, we will be having the descent diagram that I explained. So when you are getting the failure points, the failure points will be scattered here and there in the graph. So when it is scattered here and there, we will be taking a one mean line. So and two straight line conditions are Soderbergh and Goodman line, and one is parabola is Gerber parabola. So usually for the engineering calculations, theoretical and for everything, compare with the parabola and the curvy line. So we will be prefer the straight lines. So here we are going to see that a Goodman and Soderbergh line. So now fatigue under fluctuating stress. So atmospheric turbulence. So some unconditional conditions, unexpected conditions, and due to that landing, so vibration. So many conditions in the aircraft if you are taking. So many conditions will be there. So sudden gust loads. So due to that and all, you will be getting that more fluctuating stresses. So atmospheric turbulence on the cabin pressurization cycle are only two many fluctuating stresses that cause damage in the aircraft. On the ground, the wing is supported on the undercarriage and experiences tensile stress its upper surface. But during flight, it is different. Bottom surface, lower surface will be experiencing the compressive stresses. In flight, the stresses are reversed. So lower surface will be experiencing the compressed due to that because it needs to support the wing. So also the impact of landing, ground maneuvering on imperfect surfaces cause stress fluctuations. So imperfect surfaces, not even surfaces, during that time it will be experiencing the fluctuating stress while during landing and takeoff. Flaps are lowered and raised, production additional stress in the flap support structure. Engine pylons are subjected to fatigue loading from thrust variations in takeoff and landing. So these are only some basic conditions when you will be experiencing, the aircraft will be experiencing the fluctuating stresses. So fatigue failure occurs under fluctuating stresses over time. So Goodman and Soderbergh criteria help predict failure under such loading. When you are having it more fluctuating stresses, at the time Goodman and Soderbergh equations or lines will be giving the how to predict the failure. They relate mean stress and alternating stress. That is the your stress amplitude with material properties. So alternating stress refers to a type of cyclic stress that reverses in direction during repeated loading and unloading of material. So cyclic stress I explained. So we'll be having that your mean stress, compression and tension bending will be there, and sometimes we'll be having that during the loading condition, and when you are removing the load, unloading conditions, it will be having the difference. It typically varies symmetrically about a mean stress level, often zero, and is a key factor in a fatigue failure of materials. So especially in rotating machinery, aircraft structures and components subjected to vibration. So mean stress outside already I said. So mean stress is nothing, the average of the maximum stress and minimum stress in a loading cycle. So it represents the baseline or central level around which stress fluctuates in a cyclic loading scenario. So this is that here in this condition. So we are taking this is that your mean stress point. So below after this it will be having a tension. This is compression. So this is that your variable stress, that is means your stress amplitude. So sigma A, and this is that your sigma M. So this is nothing variable stress. As I said, the difference between the maximum and minimum, the average difference. So sigma max minus sigma minimum divided by 2. This mean stress is nothing, your average of maximum and minimum stress. So left side will be getting that fully that compression point. It will be similar only. So now this is that right side is tension. So Goodman uses ultimate strength, less conservative, brittle failure mode. Why we are calling it brittle failure mode, ductile failure mode? You can see the line here for the Goodman. It is connecting with your, this is that your ultimate strength. There is no yielding point. So yielding level sigma y is connecting with only Soderbergh. So when you are having that yielding, only then the brittle material will be having the yielding nature. So for that only Soderbergh is suitable for the brittle material, so ductile material, and Goodman uses ultimate strength. So it will be not having any yielding point anything. So it will be directly going the ultimate strength. So it will be having that your brittle failure mode. So equations help safety against fatigue failure. So this is that you are generally from that fluctuating stresses. So you'll be having that Goodman line and the same diagram only. So sigma W, and you'll be having that yield strength. Up to yield strength it is with Soderbergh line. Up to ultimate strength it is your Goodman line. So this only in the material point of view will be telling. Soderbergh is for ductile mode. Goodman is uses that failure brittle failure mode. And Goodman-Soderbergh diagram is an equation used to quantify the interaction of mean and alternating stresses on the fatigue life of a material. So mean stress, you can see that sigma m is equal to sigma max plus sigma minimum divided by 2. Similarly, alternating stress, that is that your stress amplitude, sigma max minus sigma minimum divided by 2. So your endurance limit is your sigma e, and yield strength and ultimate strength, these are the points. So Goodman equation is sigma a divided by sigma e, that your alternating stress or stress amplitude divided by your endurance limit plus mean stress divided by ultimate point. This is that equal to 1. So it is equal to 1. If it is less than 1, it is safe. If it is greater than 1, it is unsafe condition for the failure will occur. So that is that your is equal to 1. Then next Soderbergh equation, it is as already in the previous line we said, Soderbergh will be connecting with your yield point. So Goodman is connecting for your ultimate point. So only difference is here instead of ultimate stress for the Soderbergh you will be having sigma A divided by sigma E plus sigma M divided by sigma Y. Yield strength is equal to 1. So these are the Goodman equation and Soderbergh here, but here we are not considering pairs. Next conditions will be there. So with the factor of safety, without factor of safety. When you are considering the load factor and the factor of safety, this equation will be slightly modified with, you will need to consider, this is without considering the factor of safety and your load factor. Right, now for the same basic example, So during cruise, a wing spar of a light aircraft experiences cyclic loading due to gust encounters. So the maximum and minimum normal stresses recorded are 220 megapascal and 80 megapascal respectively. So take endurance limit is 200 megapascal, your ultimate strength is 500 megapascal, and yield strength is 350 megapascal. So now from this, you know that a Goodman equation is, so in a previous thing we have seen that, so Goodman and Soderberg equation, this two equation only we are directly substituted here. So sigma A divided by sigma E plus sigma M divided by sigma U, that is the your Goodman. So similarly, what this is Goodman, you can substitute. Now you need sigma A and sigma M. So what is sigma A? That is the amplitude stress. That is nothing. Sigma max minus sigma minimum divided by 2. Your mean stress is sigma max plus sigma minimum divided by 2, right? So now this sigma stress and amplitude and your mean stress you can calculate. So that only we are calculating here. So sigma mean is equal to sigma max plus sigma minimum. It's nothing, 220 megapascal plus 80 megapascal. If you're adding that, you'll be getting 300 megapascal divided by 2 is 150 megapascal. That only directly we are substituting here. So mean stress is 150 megapascal. Similarly, sigma max divided by minus sigma minimum, that is 220 minus 80 is 140 divided by 2 is 70 megapascal. So now you can directly substitute in that equation, Goodman and Soderberg equation. So you will be getting that 70 divided by 200, 150 by 500 is equal to 0.35 plus 0.3. You are getting the 0.65. So now this equation is equal to 1, right? So as I said, if it is less than 1, you are getting, that is safe condition, right? So if it is greater than 1, it is unsafe. That we'll be seeing one more. So the main landing gear strut of a transport aircraft is subjected to heavy dynamic loading during takeoff and landing. So it experiences a stress fluctuation from 550 megapascal to 200 megapascal. So assess the fatigue safety of the strut. If your endurance limit is 300 megapascal, ultimate strength 750 megapascal, and sigma y is 500 megapascal. So again, you have to calculate sigma mean and sigma amplitude stress, mean stress, and stress amplitude. So if you are substituting that equation, final answer you will be getting 1.02 and 1.33. So this is greater than 1. But this your condition as per the Goodman and Soderberg condition, that is equal to 1. So if it is greater than 1, this condition is unsafe, right? So this is that for predicting that failure by using the Goodman and Soderberg, but without considering the load factor and factor of safety, right? The Goodman and Soderberg relations can be used with or without load factor or factor of safety, depending on whether analyzing failure theoretically as a boundary or designing a component with margin of safety. So usually for the design, for the real component, everything always will be keeping the factor of safety. So allowable stress, that will be allowable stress and ultimate stress. So allowable stress to decide that you need to consider with load factor and factor of safety only. So the general equations define the failure envelope. What was that previous one? The boundary between safe and unsafe operating conditions under fluctuating stresses. So they are used in fatigue analysis, comparing test data, material fatigue characterization. Now, when designing a real component, so always engineers need to consider that your factor of safety, the margin level we need to fix, include a safety factor to account for. So uncertainties in loading. But suddenly in aircraft also, sudden gust load and all will come. So for that and all, it will be always will be having with the safety factor, material imperfections, environmental factors, unexpected usage. So the equations Goodman and Soderberg with consideration of your load factor. So the same equation only, sigma A by sigma E plus sigma M divided by sigma U ultimate strength is equal to 1 by N. This N is nothing, that is the your load factor, factor of safety, right? So Soderberg same similar way, this instead of equal to 1 by N. Now when you are having the factor of safety, you have to calculate what was the answer getting. So the value, when you are substituting that, you are all the altitude, stress amplitude, your endurance limit, mean stress, and yield strength. When you are calculating and adding, if it is less than this 1 by 1, then it is a safe condition. If it is greater than this 1 by 1, it is unsafe condition. So Goodman and Soderberg relationship, this only. So you can see that one blue line and red line. So the blue lines are Goodman equations and red lines are Soderberg equations. So what is that thick, thin, not a dotted line? The continuous line is that you are without safety factor condition. For thin, your with the safety factor, your dotted line condition. So you can see the difference when you are not considering that safety factor, it will be mean stress will be 400. So when you are considering the safety factor, that will be mean stress will be 200. So whatever that below this curve, below this lines, it will be a safe, considered as a safe mode. So now with the load factor or with the factor of safety, so how we can calculate a composite wing box section in UAV wing is subjected to a variable amplitude and a spectrum during surveillance mission. So measured stress fluctuates between 180 megapascal and 420 megapascal. The minimum and the maximum is 180 megapascal and 420 megapascal is the maximum. So material properties, endurance limit, ultimate strength and yield strength they are giving. So along with that factor of safety we are considering. So factor of safety is the same way only. Check fatigue safety using Goodman relation and Soderberg relation. Also compute allowable sigma A for given sigma M using both methods. Right. So now Goodman equation with factor of safety. So with the factor of safety, the left side of the equation will be same only. Only one thing is equal to 1 by n when you are considering the factor of safety. So now in the same way, how we are calculating that sigma m and sigma a, the same thing only. Sigma m is equal to sigma max plus sigma minimum divided by 2. Sigma amplitude is sigma max minus sigma minimum divided by 2. Right. So now by using this, you can calculate your stress, amplitude stress, mean stress and your amplitude stress. So by using this, you can calculate sigma A and sigma M and endurance limit and ultimate strength, endurance limit and yield point is already given. So when you are substituting that, you will be getting 0.98. Now here the condition, it is when you are taking that as a without considering the factor of safety, it is less than 1, which means it is a safe condition. But now here the limit will be with the factor of safety. So 1 by 5. So what is equal to right side 1 by n will come, right? So now the factor of safety is given 1.5. So now if you are getting this, that will be at most it will be equal to 0.666. Now with the factor of safety, the condition is 0.666 only, but now what we got, it is 0.98 and this is 1.23. Then which means default it is not safe condition, right? So the nose landing gear fork of another one numerical of a trainer aircraft is subjected to combined axial and bending fatigue loads. So resulting minimum and maximum equivalent stresses are 520 megapascal and 160 megapascal respectively. So again, the remaining all other given data is given. So now here only difference is the factor of safety is 2. So what is that? The right side will be having 1 by n, that is equal to 1 by 2, that is equal to 0.5. So now whatever that, after substituting your mean stress and your stress amplitude, if you are getting less than 0.5, then it is safe condition. If it is greater than 0.5, it is unsafe condition, right? The same thing only happening here. So after substituting all that, you will be getting 1.05 and 1.22. So when you are considering this is factor of safety, then it is more than greater than 0.5, then this is not safe conditions. Right. So the suggestions increase cross-sectional area, reduces stress amplitude and mean stress proportionally. Use higher strength materials with greater endurance limit, with greater ultimate strength and with greater yield limit. So add fillets or reduce stress concentrations. Apply surface treatments. So for example, doubling the cross-sectional area reduces both your amplitude, stress amplitude and mean stress by 50%. So now when you are increasing that area, so you'll be getting 0.49, then it will be changing into safe condition, right? So these are all the some references for the fluctuating stresses where you can so Mexican book, you can follow it, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.